Hello everyone, to give you an idea about the previous work, I would like to draw your attention to this demonstration in which we saw that the existence of columns will decrease the level of danger until the evacuation completes. Each circle represents an agent. When the agents are safe, their color is green. When they are likely to be in danger, their color is orange. And when in serious danger, their color will turn into red. The literature suggested that the symmetrical existence of columns results in a higher level of safety. The next question is then to ask, what would be the best asymmetrical column layout? Crowd simulation is not new. There are even algorithms and software to do that. However, these softwares and algorithms do not work in design platform. In this video, the main idea is to apply genetic algorithm in conjunction with our previous crowd simulation model to suggest the best parameters for the building elements which we put them in question. I have simplified the geometry in a manner that two sliders change the position of the columns. This is a demonstration of how the simulation works. Each of these sliders is a chromosome. Together, these chromosomes will create a genome. To apply genetic algorithms, we need to have a fitness function. The fitness function evaluates the performance of a given layout. In this presentation, it had been set to minimize both the required time for evacuation and human dangerous collisions. The number of iterations that are required to evacuate the building will serve as an estimation of time. Since the iteration will continue until the relaxation of the crowd, we need to deactivate the toggle when the last individual evacuates the building. Toggle is the input of the congruent physics engine, and we will understand the time that is required to deactivate the toggle from the output of this engine. There is no way to feed the output into the input in Grasshopper. To make it possible, I saved the toggle into a text file, which Grasshopper reads its content to set the status of toggle. A VB node will understand when the evacuation is completed and will set the content of the same file into true to deactivate the toggle. This is a demonstration of that. In calculating the number of collisions, we may want to give more weight to the number of serious injuries compared to the number of those who are likely in danger. In so doing, I have multiplied the chance of occurrence of serious injury by 5 and then added it with the chance of occurrence of likely in danger collisions. Finally, I added the resulting value with a constant value so that in cases where the likelihood of occurrence of any kind of injury is 0, the algorithm still tries to minimize the time. At the end, the formula would look like this. Galapagos is one of the Grasshopper's native batteries that runs genetic algorithm to find an optimized solution. Before using it, let's review the data stream inside the Grasshopper's model. The Grasshopper batteries and wires are live streams of data. It means that data is constantly moving through wires and batteries like an electrical current. Let's start with the genomes. Chromosomes are connected to a VB battery. This battery saves the chromosomes in text files on the hard drive. It constantly reads the text files and compares the input chromosomes with the contents of the text files. When the input chromosomes are the same as the contents of the text files, it returns the value of the text files. When the input changes, whether manually or by an action taken by Galapagos, this node will first update the content of the text files to the new chromosomes, then it will return the value of the text files, which are the new chromosomes, and finally activates the toggle. With the new genome, the building layout will be updated and the Kangaroo physics engine will start running the simulation. During the time when the toggle is active and the simulation is in progress, the chances of injuries will be recorded in real time using VB batteries. When the last agent leaves the building, the toggle will become deactivated. Then the recorded data of injuries will be fed into the fitness function to evaluate the performance of the genome. With this setting, we can use Galapagos battery to suggest the next genomes. Let's see how it works. You can see here that Galapagos changes the chromosomes in time intervals when the crowd simulation is still running, which means the new fitness values were not produced. I wrote a VB node which returned the null value when the crowd simulation was still active. However, Galapagos interpreted null as 0 and kept working. I did not find a way to control the time interval between suggesting new chromosomes so that I could make Galapagos to function well. There are a number of possibilities for this failure. A time span might be required to update the plan layout before running the toggle. Similarly, another time span is required to put Galapagos battery on hold until the new fitness value is produced. We expect to stop the transition of data to Grasshopper battery when the Kangaroo physics engine is running. We can develop a Grasshopper VB node which takes a value and returns it after a specific time interval. Nevertheless, it does not postpone the activation of toggle or transition of data. Placing this so-called postponing node will freeze the data stream in the entire GH file. Now we have ample reasons for using an external application which could implement the genetic algorithm and communicate with Grasshopper. We hope that postponing the time could be done somewhere outside Rhino and Grasshopper. I developed a Visual Basic program which talked with Grasshopper through both writing and reading text files. Using this program, we can at least be convinced that we can control the time spans for updating the geometry and running the simulation from outside Grasshopper. I validated this VB program by comparing its results with the results of Galapagos battery in a simple case. I realized that both of them were suggesting the same results. This validation makes us confident that the VB program is functioning well. The simulation ran for 1.5 days, after which the difference between the fitness values was not significant. The number of individuals on each generation was set to 40. 12 genomes were made out of mutation in the next generations. The algorithm worked for 14 generations to evolve the genomes. The percentage of mutation was set high to get better results. This high percentage, however, will make the interpretation of evolution difficult. Therefore, in the following graphs, I will remove all of the mutations. To make the interpretation of evolution still easier, I will also use a moving average trend line, which to some extent dissolves the variation. As expected, the fitness value is decreasing across generations. The moving average trend also shows that the fitness value becomes less noisy and more consistent. The pattern of evolution of chromosomes clearly shows that they are evolving. They are both converging and losing their noise. Serious level of danger shows a noisy pattern of decreasing. The moderate level of injury neither decreases nor increases. even there is not a significant change in the noise level. No wonder why moderate level of injuries change less compared to the serious injuries, since in the fitness function we considered serious injuries 5 times more important. The required time for evacuation also does not change its trend across evolution. We can indicate that the time for evacuation does not significantly change with the changes in the position of the columns. It is likely that the results of our simulation be trapped in a local minimum. Unless we run the simulation for several times, we cannot claim that we have found the best results. What could be concluded from this result is that one of the best genomes that offer the best setting for the building evacuation has an asymmetrical chromosome structure. Summing up, this conclusion also receives support from the literature in this area. In addition, our method is capable of suggesting one of the best sets of parameters for building evacuation in panic situations.